it'll be easier for me to break it up that way to that. Yeah.
All right. So let's talk about the next step. So, all right. Where were we? So, so that's an example of what we're talking about with the multiplication rule. Let's move on to the addition rule. So, so I have if A and B are defined on a sample space, then we have the probability of A or B. We add the probabilities, and then we subtract this probability of A and B. And we've been kind of building you up to this point. I've been trying to talk about what that actually is doing. So the probability of A and B there, subtracting that off is actually because we double counted. So there's the possibility that with A and B, there is some overlap between those two sets. And if I just calculate the probability of A and calculate the probability of B separately, kind of thing, then I'm possibly double counting that group that is both in A and B. And so I have to take away this A and B because we double counted. It's not like we had an issue being able to count or something like that. It's just the way we work this, it happens sometimes, double counting, because we double counted. Counted. There should be an in there somewhere. But then again, if we had mutually exclusive events, right, totally separate groups, no overlap whatsoever, it doesn't really matter, and we'll get this condition where the probability of A and B is just 0, and then our formula decreases a little bit and gets a little bit easier. You really just do add those probabilities together. But you have to know they're mutually exclusive events. We have to know that to be able to do that. So, yeah. Yeah, so the mutually exclusive events, totally separate circles, right? But if I had some overlap, right, no longer mutually exclusive, though that group in the middle is being double counted. So when I just add these two together, so I have to take that out, try and say, okay, I don't want to double count those.
And then also, reverse if you see these before that, or you just think of that.
Yeah. Yeah, and there's no issue with following these statements. I'm not a big fan of writing multiple formulas because I hate wasting space on my cheat sheet, and not only that, in my head as well. So this formula and this formula are the important ones. Nothing's going to go wrong if you have those formulas. It's just on this one you'll get, if you try and calculate this one, you're going to get that fact that is just the probability of B when you're talking about independent events. Or if you're trying to calculate this one, right, you'll just get that this is 0 when you're trying to calculate when they're mutually exclusive. So they work either way, right, whether you're talking about independent events or mutually exclusive. So why waste space in your brain?
So the one that the rule may also be rewritten is the easiest way to remember. Is that what you said?
Yeah, so the ones I boxed there. Okay. So either, I don't know why I boxed that one, but the one in the top two is fine. Either way. All right.
Okay.
So let's go for example. So here we got Carlos plays college soccer. So let me move this up.
I need a little clarity before we do this.
Yeah. Mm-hmm.
So when we're trying to calculate a problem, if we see the probability A and B, A to me means that it's something shared. So then that means I want to use the multiplication rule. If I see the probability is A or which is generally all,
yeah,
then I want to do the addition rule.
Yes. Yeah.
Easy way to remember?
Yes. Yeah, so, and I forgot to say that. I did that in my last class when we were talking about multiplication rule. I usually correlate multiplication to the and statement.
Okay.
So this is and when I talk about addition rule, this is or. I did this in my other class, so thank you, Joel. I forgot to do it here. So we think or for addition rule and for multiplication rule. So those statements are what we're going to be trying to do when we get to these word problems that, right, we're throwing words involved. And we got to think, is this an and statement? Am I saying, is it this group and that group? Is it the probability of getting an ace of hearts and a king? Or is it an or? So that's what we have to decide. So one's easier than the other. Right? It's harder to get the and statements than it is the or statements. So, all right. So Carlos plays college soccer. He makes a goal 65% of the time he shoots. Carlos is going to attempt 2 goals in a row in the next game. Good job, Carlos. A equals the event. Carlos is successful on his first attempt. E equals 0.65. Does that make sense? Carlos's probability of making a goal, right, is 65% of the time shooting. If A is the event, Carlos is successful on his first attempt, then his probability is 65%. That's all it's saying. It's saying essentially the same thing, though, just writing it into that notation of P of A. P of A equals 0.65. Then we got this other event, B. B is the event, Carlos is successful on his second attempt. P of B is also 0.65. So Carlos's probability is 0.65, whether it's his first attempt, second attempt, or whatever attempt he's got. So Carlos tends to shoot in streaks. The probability that he makes the second goal given that he made the first goal is 0.90. So that's awesome, Carlos. So what we're talking about there, right, and we're bolding the given to make it really obvious there, is the probability that he makes the second goal, which is our B statement, given that he made the first goal, which is our A statement. So this, what we were just given here, is the probability of B given A is 0.90. So given Carlos makes the first goal, what's the probability that he will make the second goal? He's got 90% of the shot. So it's kind of like a hotness factor in what we're saying. We've heard of that term before. They talk about it in terms of basketball a lot. You make one shot, right, and then you're more likely to make that next shot kind of thing. Although I think they actually proved that that's not true anymore. I think there was a big study on this. So, but we're going to work this as if it was true. So we got this hotness factor. So let's talk about what we want to accomplish here. I want the probability that it makes both goals. So both A, how would I say this? And not A or B, B. Both goals. The first one and the second goal. You get the words? So I want to calculate the probability of A and B. Well, we have a formula for that. We have a formula for that using this B being in the front, A being second there. I want to think about the formulas we wrote down earlier. So I know I have to use the given condition of what we have there. And I'm going to multiply by something in the front. What am I going to multiply by? Not the complement. So just look above, right? We're trying to decide what goes there. P of A. Because A is in like the denominator here, so we want that there. Just by what we discussed on the top of this page, right? And how we want it. Does it really matter in this case? No, because P of B is the same as P of A. So if we messed up here, it probably wouldn't matter. So because we know what these probabilities are, P of A is 0.65, and then we're going to multiply by this hotness factor, this 0.90, and I'm going to get something I don't know. I need some help now. 0.65 times 0.585.
Yes.
Yeah, you getting that? What's that?
Oh, I'm trying to figure out why this paper I do it and it multiply.
Because what we have here, what the given statement says, probability that it makes a second goal given that he made a first. So we have this statement. So since I have this statement, I have to figure out what I'm multiplying by.
Oh, and that's the, okay.
With this second one being A, that first one should be the probability of A. I'm trying to match up the formula with what I got. Right, just to be careful, in this case, it actually wouldn't matter if I had the probability B first there too, which is kind of problem, so. Because it would have been the same, it would have worked out to be the same if I had accidentally put P of B there, but
Numbers were the same.
it's kind of not correct in that sense, if that makes sense. All right, so as Carlos has a 58% of the time to, when he makes, right, so makes the first goal and the second goal, 58% of the time. What is the probability that Carlos makes either the first goal or the second goal? So there's P of A or B. So now we're going to add them. P of A plus P of B. That's it. Minus. Yeah, to minus that P of A and B. It's not mutually exclusive. Sorry, I shouldn't have given that away because that was on the bottom of this page. Right, these things, right, since this is not 0, we have to subtract this portion off because we are essentially double counting the amount of goals he's going to make in these groups. See, harder to see that double counting feature, right? But it is that double counting feature. So probability of A is 0.65, probability of B is 0.65, probability of A and B is 0.585, which we just calculated. If I add these, by the way, just to point out, if I were to forget this subtraction, if you added those, I would get 1.3 as the answer. How could I tell that's wrong? It's too big, right? We don't get probabilities over 1. That'd be 130% chance that Carlos does this. He's not that good of a rock star, right? Kind of thing. It might be good, but that's too good. All right, so hopefully you can tell, right, something's wrong when you're over that the probability of 1. Nothing can be over that.
That's how you know that that's true, you must subtract.
Possibly, yeah. So that won't happen on every case, right? Kind of thing. When these probabilities are smaller and you're adding them, right? You won't see that. Oh, I went over 1 kind of scenario. So, but if it has happened, you know something's wrong, something's off. All right. So what do I get if I do these two? Sorry, what was it? 0.715. 0.7. Did we get that? Yeah. So 71.5% of the time, we could expect Carlos to score either the first goal or the second goal. Bigger probability than the and statement. That will also always happen. All right. So third question, are A and P independent? No? So the probability to define this, we would say the probability of A equals the probability, I don't want this one. No, I want the other one. The probability of B really equals the probability of B given A. Is this true? Right, like I said, this independent thing, we need to be able to write these statements to try and see if they're true or not. Or are these two things equal? Yeah. Okay. It could be, yeah. Right? And so this is just a decimal, right? 71.5%. So, yeah. Lauren?
Why did you write it?
Thanks for asking that question. I did say something. I started using A, and then I switched, huh?
Well, just up at the top it says if A and B are independent, then
Mm-hmm.
A and B equals A.
Mm-hmm. So I could have written less like this. Right, that's the same statement as what was up above. Yeah, that's true too, but there's a problem with this statement for our problem. I have this probability. I have the probability of B given A. I don't have the probability of A given B. So I gotta be a little careful, right, in what this states. So making sure that we understand that this should be equal to the probability of B because I don't have the probability of A given B. So I gotta use, not that one, but probability of B equaling the probability of B given A. This is 0.65. This one was, what was that? Oh no, that was the and statement. 0.90 was given to us. These are not equal, so it means not independent or dependent is what we could call it. So since these are not equal, right, it implies not independent. So I think this is the last question. Might be something on the other side. If, oh, sorry, Nas.
I just
Let's
have
see
a
over there.
question. I guess I'm a little confused about part B because
Mhm.
it's 65 plus 65. How come P of A and P of B aren't different anymore, like how they were last time?
They are not different because these are, I know, because that's what it's just telling us.
Okay, 65.
65, 65. So it's telling us what these probability,
Okay,
we're
got
given
you.
those.
Okay, so we're
too.
just looking for
Yeah.
those in there.
Yeah, so we're given Carlos's probabilities in this case. All right, so if are A and B mutually exclusive, what does that mean? Mutually exclusive, we have a formula. It's up above. Yeah, so A and B, probability of A and B equals 0. Is that true? I'm asking a question here, so I'll put a little question mark. Are these two things equal? No, where is it? There it is. A and B was this, was 58% of the time. It's not close to 0 at all. So these are not mutually exclusive. Not. No. So, not mutually exclusive. Not ME. That's what I'll say. I'm going to ask you something similar on the test. Right? We have some on the homework like this too. I'm just asking you, right? We gotta make this statement. Mutually exclusive means these things are equal. Right? Independent means these things are equal. Right? If you don't have those things, then it's the opposite. Right? You say no. And you're done. Right? Or if I tell you they're independent, if I give you that these two events are independent, then you know these two things are equal. Or these two things are equal. Both of them technically. So, or if I tell you they're mutually exclusive, then you know these two things are equal. Sorry.
Just in
thanks.
case we forget.
Yeah, so mutually exclusive means these two things are equal. Independent means these two things are equal.
So that's why you crossed it out.
Yeah.
Okay.
Not in this case, right? So
Right.
this I crossed out because